Hello. Welcome back to the Universe series by Vi Discovery. Supermassive black holes are some of the most incredible, terrifying, and mysterious objects in the universe. They reign supreme at the centers of most observable galaxies, where even gigantic stars meet their end. An average black hole has a mass 3 to 10 times that of the Sun, and a diameter of its event horizon ranging from 18 to 60 kilometers. However, a supermassive black hole can be millions, even billions of times heavier than the Sun. As of October 2024, the king of black holes is Phoenix A, weighing in at a mind-blowing 100 billion solar masses and spanning a diameter of 590 billion kilometers. Just to give you an idea of its vastness, NASA's New Horizons spacecraft took 9 years and 5 months to travel from Earth to Pluto, and Phoenix A is 100 times wider than that entire journey. For anyone who's never flown on a spaceship before, let me put this into perspective. If you were to fly from one end of Phoenix A to the other in an airplane, it would take you over 70,000 years. If you started in the Ice Age, you'd arrive in the year 64,676. Supermassive black holes are the single heaviest objects in the entire universe. To create something with such unimaginable mass requires a tremendous force, and so far, even the sharpest minds on the planet haven't fully figured out how these colossal masses form. If you've watched a few black hole videos on YouTube, you might think that supermassive black holes are just stellar black holes that hit a big growth spurt. That logic sounds good, but it doesn't really hold up when you dig a little deeper. Stellar black holes form when a star collapses, and they usually have a mass ranging from a few to several dozen times that of the Sun. Sure, they can grow by consuming nearby matter, but in reality, this process is incredibly slow. Why? Simply because there isn't a lot to eat in space. The average distance between any two stars in the Milky Way is about 5 light-years, or roughly 47 trillion kilometers. Even in the densely packed centers of galaxies, stars are still separated by about 0.013 light-years, which is 860 times the distance from the Earth to the Sun. On top of that, there's another factor that keeps black holes from growing too fast: the Eddington limit. When a black hole consumes too much too quickly, the material in the accretion disk heats up so much that it produces intense radiation. This radiation blows away the surrounding matter, effectively slowing down the black hole's eating speed. Under ideal conditions, the Eddington limit allows any black hole to double its mass every 100 million years. So, a stellar black hole starting at 30 solar masses would take 2.5 billion years to reach 1 billion solar masses. But scientists have discovered quasars, ultra-bright galactic cores powered by supermassive black holes, already exceeding 1 billion solar masses when the universe was less than 1 billion years old. This suggests that supermassive black holes must have started from something heftier right from the get-go. During the cosmic dark ages, gigantic gas clouds, ranging from 100,000 to 1 million solar masses, may have collapsed directly into enormous black holes. These massive black holes then accumulated surrounding gas and merged with other black holes, eventually evolving into the supermassive black holes we find at the centers of galaxies today. The tricky part is that when a gas cloud collapses, it tends to cool down rapidly and break apart. Each fragment then forms a single star, much like our own Sun. Another theory suggests that the seeds of supermassive black holes were born in the chaotic conditions of the early universe, just a trillionth of a trillionth of a trillionth of a second after the Big Bang. In these moments, ultra-dense regions of space collapsed into primordial black holes, with masses ranging from a few grams to millions of solar masses. The frustrating part: we haven't yet found any evidence of these mysterious entities. But what if I told you that the real origin of supermassive black holes isn't from the collapse of any ordinary matter at all? Instead, it could come from an invisible dark realm within, a phenomenon scientists refer to as a dark star. You see, what we call ordinary matter, you, me, planets, stars, and galaxies, actually isn't that ordinary at all. It's incredibly rare, making up just 5% of the universe's content. We should probably start calling it special matter, don't you think? So, when scientists observed galaxies, they realized something pretty mind-boggling. After counting all the stars in a galaxy, and even factoring in the supermassive black hole at its center, they ran the numbers through a computer simulation. The result? The gravity from all the matter in the galaxy isn't strong enough to hold it together. So, they looked at the empty spaces and thought, there's gotta be something there. Like an invisible framework that's keeping hundreds of billions of stars glued together. That something is what we now call dark matter. It's called dark because dark matter doesn't interact with any electromagnetic radiation, including light. According to calculations, every galaxy in the universe needs about 5% ordinary matter and 27% dark matter to maintain its structure. The remaining 68% of the universe? That's dark energy. Dark matter clearly has mass, and it interacts with gravity, but it doesn't interact with ordinary matter or light. That's why we know it exists, and even where it is, but we can't actually see it. Scientists hypothesize that dark matter could be made up of particles called WIMPs, weakly interacting massive particles. They're called weakly interacting because WIMPs only interact through forces as weak as or weaker than the weak nuclear force, including the weak nuclear force and gravity. The cool thing about WIMPs? They're super antisocial. Every WIMP is its own antiparticle, and when two WIMPs collide, they can annihilate each other, releasing energy and creating both matter and antimatter. Stars like our Sun exist in a delicate balance between two forces: gravity pulling inward and the energy from nuclear fusion pushing outward. These two forces balance each other, giving us a free energy source for billions of years, until the fuel for nuclear fusion runs out. At that point, the force opposing gravity disappears, and massive stars collapse into black holes. But what happens if you add dark matter into the mix to stabilize things? You get what's called a dark star. Before we dive deeper into dark stars, have you ever wondered why we don't see stars with thousands or even millions of solar masses? Why can't a supermassive black hole form directly from the collapse of a single, ultra-massive star? Here's the thing. Regular stars, like the ones made from ordinary matter, live thanks to nuclear fusion, where lighter nuclei are fused into heavier ones. This fusion reaction only happens when the matter at the star's core is crushed by gravity. If a star has too much mass, the fusion reactions become so intense that they can blow away the outer layers of the star, which limits the maximum size a star can reach to just a few hundred solar masses. But what if a star contained a bit of dark matter? It wouldn't need to be squeezed so tightly to ignite a fusion chain reaction. Instead, the energy that balances gravity would come from the annihilation of WIMP particles, those weakly interacting massive particles. Dark stars wouldn't be made entirely of dark matter, though. If they were, they'd annihilate themselves too quickly. Let's rewind to the early days of the universe, around 80 to 100 million years after the Big Bang. At the heart of proto-galaxies, vast clouds of hydrogen and helium formed alongside dense pockets of dark matter. As these clouds cooled, they began to collapse, dragging dark matter along with them. As the density increased, dark matter particles started colliding more frequently and annihilating each other. This released energy, heating the clouds and preventing them from collapsing completely into a core where nuclear fusion could ignite. Unlike ordinary stars, dark stars draw energy evenly throughout, rather than just from their core. The surface of a dark star can reach temperatures of up to 9,700 degrees Celsius, almost twice as hot as the Sun's surface. Yet, overall, they're still considered cool, especially compared to the Sun's core, which burns at a scorching 15 million degrees. Dark stars are massive, diffuse, and incredibly bright. Because they don't need to be crushed by gravity to trigger nuclear fusion, they can exist stably on an enormous scale, far larger than regular stars. With enough dark matter, a dark star can grow to the size of the entire solar system, with a mass millions of times greater and a brightness up to 10 billion times that of our Sun. I know you're probably wondering, how does this even work? Dark matter is invisible to any kind of lens, meaning no matter how massive dark stars might be, we shouldn't be able to see them, right? Well, that's true to an extent. But when dark matter particles collide and annihilate, they release energy that heats up the surrounding gas, making it glow like an ordinary star. Over time, the dark matter gets used up, and when it falls below the threshold needed to balance gravity, the dark star collapses entirely, forming a supermassive black hole seed. This idea was proposed in 2007 by astrophysicist Catherine Fries and her colleagues. While dark stars are thought to have formed in the early universe when dark matter was still abundant, some scientists believe a few might still survive today, and we may have already found them. In 2022, the James Webb Space Telescope detected 3 mysterious objects, dubbed dead light. At first glance, they looked like ancient galaxies that appeared when the universe was just 300 million years old, which is weird because scientists have long believed that such bright galaxies wouldn't show up until at least 1 billion years after the Big Bang. These objects shine like galaxies, but they lack the hot core you'd expect, meaning their light probably isn't coming from nuclear fusion. Catherine Fries suggested that these 3 ancient objects discovered by James Webb could be the first dark stars ever captured on camera. Spectral analysis shows they have a mass between 500,000 to 1 million times that of the Sun, and a brightness billions of times greater than our Sun. They're also massive in size, with a radius over 10,000 times larger than the Sun, far bigger than any modern star, and they appear more round and star-like than galaxy-like. But in the end, this is still just speculation. Could dark stars be the key to solving the mystery of supermassive black holes? Or are they just a fun thought experiment, a mind-blowing concept for YouTubers like us to chew on? Let's discuss it in the comments below. And as always, if you enjoyed the video, hit that like button, subscribe to Vi Discovery channel, and ring the bell for more epic space content. Until next time, take care and see you soon.